our last talk of the morning will be Daniel Alvarez talking about the construction of symplectic groupoids via reduction.
Well, thank you for the opportunity to talk about this. And, well, let me describe the goal of this talk. My goal is to describe an integrability criterion for Poisson structures that are obtained from reduction of Dirac structures, and more importantly, to give applications and concrete examples of this construction. So I will recall very briefly the definition of symplectic groupoids and its under relation to Poisson manifolds. I will say a few words about Poisson reduction and Dirac structures, and I will state the main results, and then I will give some consequences of that. So let us recall that symplectic groupoid is a Lie groupoid endowed with a symplectic structure on its total space, such that the graph of the multiplication is a Lagrangian submanifold. Symplectic groupoid can be seen as a global counterpart of a Poisson manifold in the following sense. You have the base of a symplectic groupoid inherits a unique Poisson structure such that the target map is a Poisson map. And in this case, M is called integrable. And as everyone here knows, not every Poisson manifold is integrable. So let us move on to Poisson reduction and Dirac structures. I mean, for a purpose, Dirac structures are a tool to describe quotient Dirac structures. We can see a Dirac structure as a degenerate Poisson structure in the following sense. If a Poisson structure is determined by symplectic foliation, a Dirac structure is determined by a presymplectic foliation. So how can we perform reduction of Dirac structures? Well, we can in the same way that if we have a closed form, we can kill its kernel and obtain a symplectic manifold. If we have Dirac structure, we have its kernel, and if we can somehow kill it, we obtain a Poisson structure on the quotient. Let's recall that if a Dirac structure is given in this way, then its kernel is this intersection. In that case, L is a pullback of pi. There is a notion of pullback Dirac structure, and L can be described in this way. So the question that we would like to answer is following. When is the quotient of a Dirac structure integrable? And the second question is, how can we describe an explicit integration of a quotient Poisson structure in terms of an integration of the original Dirac structure? Well, let us first illustrate this problem with a simple and very well-known example, which is the following. On the two-sphere, we consider an array form and take a positive function. And then if we multiply this array form by this positive function, we get a symplectic foliation and this M. And so we get a Poisson structure. Now consider this is the Hopf fibration times the identity. If we take the pullback of this Poisson structure, we always get an integrable Dirac structure. But the Poisson structure is integrable if and only if the function is constant or has no critical points. And this has been proven in several ways. So the main result is the following. If we have a surjective submersion and a Poisson structure on the base, the following are equivalent. M is integrable, and its pullback Dirac structure is integrable, and the inclusion of Lie algebroids given by the tangent to the fibers is integrable by a Lie groupoid morphism with source the associated submersion groupoid. Well, the idea of the proof is to use the one direction was already proven by Higgins and Mackenzie using the pullback groupoid, and the other can be proven as follows. We can define an appropriate equivalence relation on G in such a way that that the quotient of this equivalence relation is again a Lie groupoid, and that we can interpret this equivalence relation as the orbit relation induced by an action of a double Lie groupoid on G on that map. Of course, we have a more general version of this theorem if we consider, instead of a Poisson structure, any Lie algebroid over M, and again a surjective submersion, and the statement is exactly analogous. Let us mention a particular case, which is the following. If we consider a principal bundle, then the previous result has been already used in several papers, and there are already interesting applications of that result. We can see that the existence of such a map is essentially equivalent to the existence of a multiplicative action of the pair groupoid on G. If we see this pair groupoid as a group and as a groupoid, and so if we have such an action, we can recover the phi by this formula. Well, we will use this particular example at the end of the talk. So if we go back to our previous example, we can apply this criterion to it. And well, in that case, we have to use Lie's second theorem in order to integrate this inclusion of Lie algebroids explicitly. And we can see that this map induces a suitable Lie groupoid morphism exactly in the case that we wanted, which is that one, when F is constant or has no critical points. So, well, this is. Now let's move on to the consequences of these results. Our first consequence is a new proof of the equivalence between the integrability of Lie algebroids and the existence of complete actions on surjective submersions. We can also recover explicit integration of several examples of Poisson and Dirac homogeneous spaces, recovering in particular the recent integration of Poisson homogeneous spaces of Poisson Lie groups. We can also obtain a criterion for the integrability of quasi-Poisson quotients, and well, there is also a nice relation between coisotropic reduction and Morit equivalence. I won't really talk about these first two items. I will just say a few words about the last two. So let us move on to quasi-Poisson manifolds. Quasi-Poisson manifold for a Lie quasi-bialgebroid is given by an action of this Lie algebroid on a map and a bivector field on S, such that certain axioms are satisfied. These axioms mean that bi fails to be Poisson, fails to be a Poisson bivector in a way controlled by the action. So the idea is that if this action is good enough, then the quotient inherits a Poisson structure. So we can ask, when is this Poisson structure integrable? And the answer is the following. We can define a Lie algebroid structure on a certain subbundle of the cotangent bundle of S in this way. And essentially, this Lie algebroid controls the integrability of the quotient in this sense. If this Lie algebroid action is integrable to a groupoid action on C, then the quotient is integrable if and only if C is integrable. the proof is apply the main result together with some additional trick involving double Lie group weights. So in this case, we can obtain an explicit integration of the quotient. In this way, we can lift the G action on S to a G action on the so simply connected integration of C, if C is integrable. And we can see that this lifted action is good if it was good on the base, and so the quotient becomes a symplectic group. So for specific choices of Lie quasi-bialgebroids, we recover several results. For example, we can recover the usual actions by automorphisms of Poisson of Lie groups on Poisson manifolds. We can also recover Poisson actions of Poisson Lie groups, and also we recover the original notion of quasi-Poisson G manifolds for a specific choice of Lie quasi-bialgebra. And in all these situations, the upshot is the following: the quotient is integrable if S is, there is always a Lie algebra. In all these three cases, there is a Lie algebra structure on the cotangent bundle of S that allows us to make sense of that statement. So this is the conclusion. And the first two cases have been already proven by other approaches, and the third one seems to be new. Let us see a concrete application of this third example. So if we consider the moduli space of flat G bundles of a compact connected orientable surface, and we take for example, a compact Lie group, then there is a canonical Poisson structure on this space, which is determined by this property that the symplectic leaves are obtained by fixing the conjugacy classes of the holonomies on the boundary. Such a Poisson structure is symplectic if the boundary is empty. And the basic idea for the integration is simply to consider this object. If we begin with a surface with boundary, we can double it, and then we get a moduli space which is symplectic. In that case, the pullback maps to each of the copies of the original sigma can be interpreted as a source and target map. So we can already guess that there should be a grouped structure on this guy. And well, in order to apply the previous result, let's recall that this moduli space can be seen as a quotient of a quasi-Poisson structure on this representation, on the space of representations of the fundamental group of the surface. So using these tools, we obtain this result, which is basically a corollary of this description. Well, there is only one thing to be taken care of, which is the non-smoothness of the moduli space. And so one approach is to consider this integration in the category of stratified Poisson spaces. And in that case, this symplectic stratification theorem is useful. Or we can simply forget about the singular part of the moduli space and restrict ourselves to the smooth part. And in that case, we can also obtain an integration of the associated Poisson structure in the same spirit. For example, if we choose this Lie group, then we obtain a symplectic grouped structure on Teichmüller space. Now let us talk about the last item, which is the following. Suppose that we have a Poisson manifold and two coisotropics of manifolds. And suppose that this Poisson manifold is integrable by a symplectic groupoid. Then, assuming a number of technical conditions, well, first of all, if this calligraphic C is smooth, we can see that it's a coisotropic submanifold of G. And well, there is, if these coisotropic submanifolds induce, smooth Lagrangian subgroupoids of G, and also these restriction groupoids are smooth, then we can perform coisotropic reduction of everything and obtain a dual pair. But in fact, under all these technical conditions, we can get more than that, which is this. With this, we can promote this dual pair to a symplectic Morita equivalence with the middle term as a symplectic bimodule, and where these quotient symplectic groupoids are obtained in the way that I described before, using these actions of double Lie groupoids. Well, this is, I think, it's always nice to have examples, because there is not exactly an abundance of symplectic Morita equivalences. So let's first see. Let us see a very simple example. Consider two classical moment maps with sources symplectic manifold, which induce free and proper actions on S, and consider as coisotropic submanifolds the graphs of these moment maps. Then we can consider as a symplectic groupoid this pair groupoid times the action groupoid associated to the quadjoint action. And well, in that situation, we can describe everything very explicitly, and we can see that these conditions that I mentioned before are satisfied, and so we get a symplectic Morita equivalence of this dual pair. This was already known, but there is also another example. If we begin with two multiplicative actions of this pair groupoid on a Lie groupoid, which are free and proper, then we can lift them to the cotangent groupoid, and these lifted cotangent actions are also multiplicative. So we get these maps again, these Lie groupoid morphisms. And again, we can define two coisotropic submanifolds given by the moment maps of this restricted action to the base of that cotangent groupoid, which is nothing but the dual of the Lie algebra of G. And again, we consider as a symplectic groupoid the cotangent groupoid times the action groupoid associated to the quadjoint action. And again, we can describe everything very explicitly. These Lagrangian groupoids and these restricted groupoids, and we can see that also in this case we get a symplectic Morita equivalence over this dual pair. And notice that these quotients can be very different topologically, but still there is a symplectic Morita equivalence. And well, these were the first examples that came to my mind, but certainly there must be some more interesting examples and applications of these results. And also, it would be nice to remove these technical conditions and use a language that allows us to deal with this and other situations without assuming these conditions that not some are very restrictive and limit the availability of examples and applications. So I think that we can use the language of stacks in order to deal with this construction and also with the previous result about quotients of Dirac structures. So, well, I think that's what I wanted to talk about.